Let's look at how to apply the sequence rules to real molecules. What atoms or units, so that would include a lone pair of electrons, stereochemistry, or ghost atoms, and we'll come back to that, should be compared to what? X represents the origin of the stereochemistry, and from here we will initially reflect upon a generic directed graph or digraph. Then on to specific molecules. More than one comparison would ultimately have to be calculated to get a stereochemical descriptor. But here we will just look at one generic case to discuss the methodology. So, X would be attached to atoms A and A'. We will be comparing letters and the prime letters to each other. A or A' are attached through one bond to X. The calculation is based upon each atom being saturated. Thus, the letter or letter prime leads to a further 3 letters or 3-letter prime. If A is the same as A', we move on to evaluate atoms or units attached to X by 2 bonds. So A or A' leads to 3 Bs or 3 B' respectively. If the Bs are evaluated as being equal to the B', then we will look at atoms or units 3 bonds from X. These are Cs and C'. Note that once an atom or unit has been considered, it cannot be re-evaluated because it can only be just 1, then 2, then 3, etc. bonds from X. That's to say, if Bs are the same as B', we only progress to consider Cs and C', but not As and A'. This is easy to see in this generic example, but real molecules can sometimes be more confusing. If all the Cs are the same as C', then we go on from Cs and C' to consider Ds and D'. If the same, D could lead to E. If the same, E's to F's, etc. Clearly, looking at the digraph as we progress from 1 bond linked to X to 2 and 3 and 4, the situation gets more and more complex. For clarity of the image, at this point we will drop the arrows, but the sequence A to B to C to D is still there. Whilst there are only 2 A's and A' in total, there are 6 B's and B' in total, growing to 18 C's and C' in total, leading to 54 D's and D' in total. That is a lot of atoms and units to evaluate. There is some good news. Certain atoms, such as hydrogens and halogens, or multiple bonds, will terminate a branch. So, very few molecules realize these theoretical extremes. In addition, there is a sequence that atoms or units a specific number of bonds from X must be evaluated in that we will discuss. When looking at databases of molecules that have been made where there is stereochemistry, the stereochemical descriptor is determined 75% of the time by 2 bonds from the origin of stereochemistry, here represented as B's and B'. 15% of the time by 3 bonds from the origin, so C's and C', and no other scenario, for example A's or D's, etc., exceed 5%. So most stereochemical descriptors are determined 2 or 3 bonds from the origin of stereochemistry. Let's examine some examples. We start at the origin of the stereochemistry. Here, it's a carbon. From there, we identify the atoms or units attached to it through just one bond. We show them here in digraph format. Can priority be established and from that the stereodescriptor determined? Well, rather unusually, the atoms or units attached through one bond to the origin of stereochemistry all have different atomic numbers. Thus, by the sequence rules of priority, we can determine all priorities required to identify a stereochemical descriptor. The fluoro group is the fourth and lowest priority. Then the chloro group at the third priority, followed by the bromo group at second priority, with ultimately the iodo group as first priority. We don't need to look at any additional bonds from the stereochemical origin. And indeed, there aren't any in this simple example. Next, a slightly more complex system. Let's break it down as a digraph. One of the harder skills is to determine the distance each atom or unit is in bonds from the origin of stereochemistry. Be systematic. From the start carbon, first identify all the atoms attached directly to it. There they are. They are all carbon atoms, and they are calculated to be the same by the sequence rules of priority. Thus, we can't assign a stereochemical descriptor and move on to the next atoms or units another bond further from the origin of stereochemistry. This will be two bonds from the origin of stereochemistry. For fun, I will also depict the atoms' three bonds from the origin, but as you will see, we do not have to consider them in our calculation. So, back to the identification of the red atoms' two bonds from the origin. On the left here, they are all hydrogens. At the bottom, there is a carbon and two hydrogens. At the top, two carbons and one hydrogen. And to the right, three carbons. To determine the stereochemical descriptor at the stereogenic center, we must identify all four priority groups. Can this be done two bonds from the origin? Yes, it can, due to the difference in the atomic numbers of the four sets of three atoms. The left atoms have the lowest atomic number, by all being hydrogens. The bottom atom have one carbon and two hydrogens. The left and bottom are similar, but for the left having a hydrogen and the bottom a carbon in difference. Thus, the bottom is higher priority due to the higher atomic number than the left. Ultimately, we will see the bottom to be the third priority. This is because if we look at the top atoms, two bonds from the origin, that are two carbons and one hydrogen, bottom and top are similar in atomic number, but not identical, and differ by the bottom having a hydrogen, where the top has a carbon. Top has a higher atomic number than the bottom, and will ultimately be shown to have second priority of the groups considered. Lastly, let's look at the right atoms. These are two bonds from the origin. They are three carbons, similar to the top group, both having two carbons, but for the third atom, where the top group has a hydrogen, the right group has a carbon, and thus the right group has a higher atomic number than the top group and is the first highest priority. With all 4 group priorities determined, we stop and don't have to look to the atom's 3 bonds from the origin. The stereochemical descriptor can be identified. This next example ultimately involves the study of atoms further from the origin of stereochemistry to allow the determination of the stereochemical descriptor. But the principle is the same. We start by identifying the origin of stereochemistry. Here it is, again a carbon. Now we locate the atoms 1 bond from the origin and lay them out in the digraph. Then include atoms 2 bonds, then 3 bonds, then 4 bonds, and though not required for this calculation, 5 bonds from the origin. First, we will analyze atoms 1 bond from the origin. They're all carbon, so no difference, and a stereochemical descriptor can't be determined. So we must move out further to analyze atoms 2 bonds from the origin. At the bottom, we have 3 hydrogens, but have 1 carbon and 2 hydrogens on the left, top, and right. The groups are similar, except the bottom group has a hydrogen, where the other groups, left, top, and right, have carbon. So by atomic number, the bottom group is the lowest priority. Just because we know one priority group doesn't mean we can assign a stereochemical descriptor, as we need to prioritize all 4 groups. So consideration moves from 2 bonds from the origin to 3 bonds from the origin. Here we don't need to look at the bottom group, as it already has a priority and all atoms terminated 2 bonds from the origin. The other 3 groups remain to be assigned. 3 bonds from the origin on the left, we have 3 hydrogens, whilst the top and right groups are similar, except where the left group has a hydrogen, the top and right groups have carbon. Thus, the left group by atomic number is a lower priority than the top or right group, that with the same atoms remain equivalent priority. So despite now knowing the 4th and 3rd priority groups, we still can't identify the stereochemical descriptor. So we move to analyzing atoms 4 bonds from the origin of stereochemistry. Only considering the top and right groups, the top group has 3 hydrogens, whilst the right group has 1 carbon and 2 hydrogens. They're similar, but the top group has a hydrogen, where the right group has a carbon. So through atomic number, the top group is a lower priority than the right group, and thus the top group is 2nd priority and the right group is 1st priority. With all 4 priority groups determined, we can calculate the stereochemical descriptor, and so don't have to look at atoms 5 bonds from the origin. So far, where there have been differences in the atoms, either the stereochemical descriptor can be determined from that set of different atoms, the same number of bonds from the origin in the first 2 cases, or all branches terminate except one per group that provides attachment to all atoms another bond from the origin, found in the 3rd case. What happens if more than one branch does not terminate? What branch path is analyzed first? That would be the atoms or units attached to the atom closer to the origin that is of higher priority. Let's see this in the generic scenario. If the B's don't equal each other, and nor the B primes, but B equals B prime, we have to move to the next level of bonds distant from the origin. We compare the C's and C primes attached to the highest priority B and B prime. If there is a difference, we stop there and don't study any other C's or C primes. Only if a difference is not found there, then the C's and C primes attached to the next highest B and B prime are analyzed, and if still no difference is found, do we continue with this method. One set of C's and C primes attached to one B and B prime at a time. If all the C's and C prime comparisons are exhausted without a difference identified, we would proceed to the D's and D primes attached to the highest priority C and C prime, etc. Note, B and B prime priority is now irrelevant. How about a molecule that exemplifies this concept? What about this? What would it look like as a digraph? Here is the origin of the stereochemistry. It's a carbon. What's attached to this carbon? Here are the atoms one bond from the origin of stereochemistry. Here are the atoms 2 bonds away. Here are the atoms 3 bonds and ultimately 4 bonds from the origin of stereochemistry. Returning to the atoms 1 bond from the origin. They are 4 carbons, so no difference yet. What's attached to the 4 carbons that are 2 bonds from the origin of stereochemistry? Well, one of the carbons, top group, is attached to 2 hydrogens and a bromo group, whilst 3 of the carbons, left, right and bottom groups, attached to a hydrogen, carbon and oxygen. The bromo has a larger atomic number than the highest atomic number, oxygen, attached to the other 3 carbons. So, because of the bromo group, the top group gets the first priority. However, we still can't assign the stereochemical descriptor. What about the priorities for the other 3 groups? For that, we look to the atoms 3 bonds from the origin. This is where things get interesting. First, we must look at the atoms attached to the highest priority atom of the left, right and bottom groups. The highest priority atom left, right and bottom, 2 bonds away from the origin, is oxygen. So, what's attached to the oxygen in the groups? So, 3 bonds from the origin. On the left, it is hydrogen. The bottom is hydrogen, but the right has carbon. Carbon has a higher atomic number than hydrogen, so now we can determine that the second priority is the right group. Still, we can not assign a stereochemical descriptor, so we continue. Let's try to find a difference between the left and bottom groups. We have to consider the highest priority atom 2 bonds from the origin. Now let's look at the next highest priority atom, still 2 bonds from the origin. For left and bottom, that is carbon, and follow it to see what is attached, working outwards to 3 bonds from the origin. For the left group, it's hydrogen, and for the bottom group, it is a bromo group. Bromine has a higher atomic number than hydrogen, so the bottom group is the third priority, and the left group is the fourth priority. Now we can assign the stereochemical descriptor. Top first, right second, bottom third, and left group fourth priority. Thus, we don't need to analyze out to the fourth bonds from the origin of stereochemistry. To highlight the importance of following the next bond out attachment in order of prior atom or unit priority, what would happen if we didn't do this in this example? So still analyzing the atom's 3 bonds from the origin of stereochemistry. Of all these atoms, the bromo of the bottom group has the highest atomic number, then the chloro of the right group, and then the hydrogen of the left group. This would make first top, second bottom, third right, and fourth priority left group. But this is not the case, so don't fall into the trap of doing it. Let's analyze the same molecule using the same rules with a slightly different methodology. I'm not going to depict the digraph, but use the same terminology of left, bottom, right, and top to identify the 4 groups that directly attach to the origin of the stereochemistry. The atoms for consideration will be placed in a table. Here are the factors that dictate the order atoms or units are analyzed in. The factor to contemplate first is the number of bonds from the atom to the origin of stereochemistry, with atoms closer to the origin to be considered first. The next factor is from our atom or unit under consideration, the priority of the atom or unit 1 bond closer to the origin. Here it's marked as Y in superscript, and in the table an example would be this hydrogen being considered before the bromine because towards the origin the hydrogen is attached to an oxygen and the bromo group is attached to a carbon, with oxygen having a higher priority due here to its larger atomic number compared to carbon. Then finally, we rank the actual atom or unit, here marked X, in order for consideration by priority, here. In the table, an example would be oxygen being looked at first due to its higher priority because of the larger atomic number compared to carbon and ultimately hydrogen. Here we are again, starting from the origin of stereochemistry. Let's look to the atom's 1 bond from the origin and build up the table. On the left, that is carbon. Bottom is carbon, right is carbon, and top is carbon. Now, how about atoms or units 2 bonds from the origin? Left is oxygen, carbon, and hydrogen. Toward the origin, they are all attached to carbon. This is the same for the bottom and the right groups. However, the top group is bromine, hydrogen, and hydrogen, all attached towards the origin to carbon. Moving on to the atoms or units 3 bonds from the origin. On the left group is 4 hydrogens, but for one of them, it has an attachment towards the origin through an oxygen, whilst the others attach to a carbon. The bottom group sees 3 hydrogens and 1 bromine, with one of the hydrogens attached towards the origin to an oxygen that has a larger atomic number than the carbon, the bromine and the other hydrogens are attached to. So the oxygen-attached hydrogen will be considered before the bromine. This will be viewed before the other hydrogens, also attached to the carbon, as bromine has a larger atomic number. The right group has one carbon, one chlorine, and two hydrogens. The carbon is attached towards the origin to an oxygen. This oxygen group has a larger atomic number than the carbon, the chlorine, and hydrogens are attached to towards the origin. Thus, the carbon is considered before the chlorine. That is viewed before the hydrogens, as chlorine has a larger atomic number than hydrogen. Lastly, let's briefly touch on atoms' 4 bonds from the origin of stereochemistry. They are only found on the right group, with hydrogens all attached to carbon towards the origin. If this has been laid out correctly, all that remains is to proceed down the table comparing the atoms of each group, left, bottom, right, and top, to identify differences and ultimately priorities. So, first, one bond from the origin of stereochemistry is carbon, 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 and carbon. So, all the same, no priority and no stereodescriptor. Next horizontal line down is into the atoms or units 2 bonds from the origin. Oxygen, 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 and bromine. Bromine in the top group is a larger atomic number, a higher priority than the oxygens of the other groups. So, top group has the highest first priority. We still can't assign a stereodescriptor, so we keep going. We don't need to consider the top group again, despite it also running out of atoms or units at this point. Next, horizontal line reveals carbon, carbon, and carbon. All the same, can't discern a stereodescriptor, so on to the next line. Here, there is a hydrogen, hydrogen, and hydrogen. All the same, no stereodescriptor possible, so moving on. On this line, we have the first atoms or units 3 bonds from the origin. Hydrogen, hydrogen, and carbon. Now here there is a difference. Carbon in the right group has a larger atomic number than hydrogen. Thus, carbon is a higher priority, second of all the groups. We still can't assign a stereodescriptor, so we continue going down the lines, but we don't need to consider the right group atoms or units anymore, as its priority has been determined. One horizontal line down shows hydrogen or bromine. There is a difference, with bromine in the bottom group having a larger atomic number, so higher priority than the hydrogen found in the left group. Overall, the bottom group is 3rd priority and the left group is 4th priority. Now, with all the group's priorities identified, a stereodescriptor can be determined. In summary, in isolation, a methyl group is a lower priority than an ethyl group. Then, an isopropyl group is a higher priority than an ethyl group. And finally, the tert-butyl group is the highest priority. Be careful using this shortcut. Importantly, it depends upon nothing else attached to the two branches under comparison dictating prioritization before both alkyl groups come under consideration together. We have seen it demonstrated with the stereogenic center in this molecule, giving these priorities. But it can also be useful in the calculation of the stereochemistry in this alkene molecule. Again, we have also seen that the methyl group has the lowest priority when compared to the ethyl. The N-propyl has a higher priority than the ethyl, and ultimately N-butyl has an even higher priority again. Importantly, in isolation, without something else impacting priority before both groups under consideration are compared together. We've seen its application in this molecule, allowing prioritization, but it can also be deployed in the determination of this alkene's stereochemistry through accurate prioritization. It's vital to accurately determine the stereodescriptor, to first compare atoms or units attached to the higher priority atom one bond in towards the origin of stereochemistry. So we know this to be the priority order of these substituents that are found with this stereogenic center, allowing their prioritization. This methodology is also critical in identifying this alkene's prioritization.